Howdy, y'all. Can everybody hear me? Cool. So, show of hands, how many of you have reverse engineered something from China? All right, now put your hand down if it's malware. The contents of this talk comes from a 32-bit ARM Cortex-M4 amateur radio that I've been reverse engineering in order to add new features. But it's the same sort of reverse engineering that you would be doing if you wanted to, say, break their crappy over-the-air cryptography. Or if you want to understand how the device works. Maybe you'd want to make a similar device for the same market. Maybe you want to know if you can feasibly beat their manufacturing cost. Or maybe you just want to know how something ticks. I'm joined in this work by Paula, DD4CR, Alex, who's DF8AV, and David, who's AB3TL. These are ham radio call signs. These are the licenses that allow us to talk on the air. And here in Croatia, I am 6A/KK4VCZ, which is really long and hard to remember. So today we're going to learn how to extract firmware from a null pointer dereference. But one that's unindexed. So you're only able to read from address 0. This is what happens when, say, malloc doesn't work. So it returns 0 because there's not enough memory available, but the read happens anyways. Normally, this will hit a guard page and crash, but as you'll see, that does not happen on this platform and on many platforms like it. We'll also be discussing how to reverse engineer a USB stack. The DMR radio networking protocol is sort of unique. It only has 24-bit addresses instead of, say, 32-bit addresses like IPv4 or very long ones like IPv6. We'll be discussing how to identify useful functions in the firmware image by looking for access to digital I/O. And we'll also be discussing what's unique about reverse engineering a Chinese product, because that's different from reverse engineering a Western product. And while some of the tricks are the same, other tricks vary by the culture that's making the device. We'll also be discussing some of the things that only matter when you're trying to maintain patches against something. So if you reverse engineer a single version of an application, or in this case a firmware image, it's very helpful to be able to move on to have your same changes apply to a new revision of it. And we'll be discussing how to build tools to do that yourself. And then finally, I'll be showing you how to take an ARM firmware image and run it inside of Linux as a regular command line tool. We do this by wrapping the firmware image into an ARM ELF executable and then using QEMU user to run it. And this allows us to extract libraries from inside of it. In my case, the MD380 has its own proprietary audio compression algorithm called Ambi2+. It's very valuable to be able to encode and decode audio in this format, but there are no tools for encoding it, and there's only one tool for decoding it. So by wrapping up the firmware image, I'm able to use its own audio codec in my project without having to fall back to the hardware. This is a sketch of the device. It's a handheld ham radio of the sort that might be used in a university police department or in a business. There are smaller and more expensive radios that are manufactured by competitors such as Motorola and Hytera. This brand is Tytera. It's like the minimal hamming distance without creating trademark infringement. The Tytera radios are a lot cheaper. They're on the order of $120 US or 140, 150 euro. So within the price range that a hobbyist can buy one in order to talk to his buddies over the air. And in several countries there are repeaters popping up that allow you to communicate between everyone else in the city, or even connect the repeaters in order to make international calls. So you can make a call from, say, Berlin to New York City to Knoxville, having all three people talk on the same channel without any other hardware than buying one of these radios and having a radio license. In commercial use, they're replacing the more expensive Hytera, minimum hamming distance, remember. They're designed to be confused. They're replacing the more expensive German and American radios. And then they just drop into the exact same network. So you can buy this radio and communicate with the expensive Motorola radios without having to change the networking software or the protocols or the frequencies. Everything is compatible. It has a 5-watt UHF transmitter. There's also a VHF model available. So this runs right around 450 megahertz. It has both digital and analog modes. So not only can you connect to a digital network running this protocol, you can also connect to the old-fashioned analog networks for either business or amateur use. So you can jump onto the older repeaters. And this allows you to use the radio in cities that don't yet have a digital repeater. The CPU of this device is an STM32F405. It has 1 megabyte of flash and 192 kilobytes of RAM internal to it. There's also a 16 megabyte SPI flash, which when they initially made the design was expected to only be 1 megabyte. So 15 megabytes are unused, and that gives us plenty of space to store extra things. It also has a C5000 radio ASIC chip. This chip is what does all of the actual radio stuff. So it sends a packet, it receives a packet, it modulates that packet into the radio signal. There's a separate amplifier, but this creates the initial signal before amplification. And this chip is uniquely of Chinese design. There is no Western documentation for this chip at all anywhere. A given network for this protocol, Volnet is the one that we use in East Tennessee. I know that none of you know where Tennessee is on a map, but it's a lovely place, and we have very good rakia made out of corn. Volnet is one of, I think, 3 different DMR networks that we have within the state. This map shows 6 of the networking towers, most of which are based in the east, along the mountains. And these mountains give them incredibly long range, so that you can connect to a tower that is more than 100 kilometers away from you. They're also all networked together, so if you can see any one of these towers, you can talk to people on other towers, and there are USB dongles that allow you to connect to it remotely. So you could plug one into the laptop here on stage, and I could make a call through the laptop over the Wi-Fi to this network to then be heard in the mountains to ask folks how their moonshine is distilling. One particularly nice feature about this radio is that it has an actual USB port. Most radios of this type instead have a low voltage serial port and require conversion electronics. Here, the CPU implements USB itself through one of 2 programs, either a bootloader application or the second layer application that's actually running the software that manages the radio that turns on the screen. So I reverse engineered the protocol that the official programming software uses, and this allowed me to read and write the basics of the radio configuration. So I could add new channels. There's a phone book that contains contacts both for private calls and for public calls. So, for example, I might have the number for a single individual friend, or I might have a number for the entirety of my home state of Tennessee. And by transmitting to one or the other, it gets routed to the appropriate location. But what I really wanted to do was dig into it and reverse engineer it. So I added raw packet capture. These frames were taken directly off the air, and these are the first captured SMS transmissions over DMR so far as I'm aware. I also implemented an Android app that allows me to run these extra features as I'm wandering around. Android has particularly good USB host mode, so it's able to talk to any device you like as long as the user clicks OK. You don't need a signed driver as you would in Windows. You don't need to modify the kernel or create a loadable module or run Python code as you would in Linux. You just click OK and everything works. It's the most convenient USB that's available for any platform. But in order to do that, I first had to get a copy of the firmware out of the radio. When you are reverse engineering malware or you are reverse engineering anything running on a PC, you have the advantage that you have very good debuggers. And you also have the the electronic file that you can read. So you see the .exe file, you know that if you start it, it will do something to begin the malware, and you have an easy starting point for reverse engineering. You might fight with a packer, but at some point it will be in RAM and running from RAM, and you'll have a copy of it. On embedded systems, you're very often not allowed to attach a debugger. This device had JTAG locked out, so that you were not allowed to begin debugging it. So the way that I dumped the firmware was through a null pointer dereference. So in Windows, when you have a null pointer dereference, that alone is not exploitable because you don't have anything at that address. You need to either create something at address 0, which you're very often not allowed to do, or you need to have an index that allows you to say, no, the buffer is at address 0, but I want something that is 1.5 gigabytes further than that in order to read off the end of the buffer. Here I don't have an index, and I'm not allowed to allocate anything new in memory, so I have to go with what's already there. Luckily, I'm running on an ARM Cortex-M4. This is an embedded 32-bit machine. It's running the thumb instruction set. And inside of the programming for the radio, you have to specify which memory you would like to read or write. The idea is that you're allowed to read from external memory, or you're allowed to write to internal memory. And when you write to internal memory, you're doing a firmware update, and the firmware updates are encrypted. I didn't have the encryption keys. But as I was implementing the code to load an encrypted update, I found that it spat back at me the beginning of the ARM firmware. And the reason why it did that was that there is no trap page loaded at address 0 in this architecture. Instead, and just for convenience, they put a duplicate copy of whatever memory you booted from. In this case, of internal flash memory. So when it was reading from a buffer that wasn't yet initialized, when it was reading from the null pointer, it was reading the very beginning of its bootloader and giving me a copy of it. Now, in the MD380 protocol, you first specify which memory, and then you read the pages from it. All I did was forget to specify the page, and it gave me back the code accidentally. But I wasn't allowed to do multiple reads because they would all come from the same place. So this only got me the first 48 kilobytes of flash memory, and nothing after that. Luckily, the first 48 kilobytes are the bootloader that decrypts the firmware updates in order to install them. So not only does it have the keys that I need to decrypt the firmware updates, it also has it's symmetric crypto, so it's also what I need to re-encrypt them. The very first thing that it does when it starts up is it locks out JTAG so that you're not allowed to read a copy of anything in memory, you're not allowed to attach a debugger. So I patched it by changing 1 byte from A5 to 5A. And what this did was it prevented the chip from locking. So now when it boots up, it runs exactly the same software. I can install the firmware update. It will decrypt the firmware update and put it into flash. And then I can attach a debugger and dump a copy of it out. So then I gave a copy of both the encrypted and the clear text firmware to my friend Paula, DD4CR. And what she discovered was that they were using AS counter mode, but they were resetting the nonce for every single frame, for every block of flash memory, which means that they were effectively using exclusive OR. And you could just XOR the firmware update with the clear text firmware in order to get a copy of the XOR string that they were obfuscating the firmware with. And then you were able to encrypt and decrypt firmware. So you can now take any firmware update and you can go back to the clear text firmware image, change it, and then write it back as a regular firmware update to be installed with the regular Windows software. So at this point, you have a copy of the firmware, but you need to figure out what it does and you need to change things inside of it. So you need to figure out how to reverse engineer it and separately how to patch it. When you reverse engineer it, you have the advantage that even though it's this large chunk of code, automated tools will sort of tell you where things begin and end, you need to know where to place them. So inside of the data sheet for this chip, and the CPU is a Western chip with full documentation in English, you'll find a memory map that shows you that at any address that begins with a 4, that's an I/O region. Anything that begins with a 2 is SRAM, which is the slower type of RAM. Anything that begins with a 1 is tightly coupled RAM, which you're not allowed to execute, but it's a bit faster than SRAM because it's connected directly to the data fetch path instead of to the memory cache. You'll also find that anything begins with a 08 is in flash memory, and because the first 48K are taken by the bootloader, the actual application begins at 0800C000. You can then load it into IDA Pro as a binary image beginning at a known address for a known architecture, which is ARM little endian 16-bit. 16-bit refers to the instruction width, not the register width. So this is still a 32-bit CPU. It's just in the denser instruction mode. In Radara 2, which is a free competitor to IDA Pro, you can load it with this command line, just telling it that it's ARM, that it begins at a particular address, that it's 16-bit mode, and that this is the image. And then you begin to reverse engineer what the individual functions do. Now, when you're reverse engineering PC software, you have clues such as system calls. So you can look at anything that calls the right system call. That has to involve I/O. You can also look at shared libraries. So if it's calling printf, you know that it's going to print something to the screen. You can then look for error messages in order to figure out what particular functions do and work your way backward from that. But on an embedded system, you can't do that because there are no symbols distributed in the product. Everything is perfectly statically linked, and there aren't any system calls because there is no operating system. So what you do instead is you realize that each register has a documented address. For example, I'm interested in the code that reads and writes the flash memory. I know that the flash controller begins at 4002 3C00, and that at 3C15, you have the actual protection register that needs a password written into it in order to unlock flash for a write. So if I look for any accesses to those two addresses, I can find the code that unlocks flash memory before writing it. And in this way, I can identify the code that rewrites the chip's own memory. Similar addresses exist for every serial port, for every I/O address of every kind, also for clocks, so you can tell when the thing is going faster or slower. It might speed up in order to do the audio codec conversion, and then slow down to save power when it's only idling and listening. And by searching for these addresses, you can find like the functions that matter. You can also look for unique masks. So the Cortex-M3 has 32-bit wide registers, but the DMR networking protocol has 24-bit wide addresses. Think of it as like a B block dedicated to the protocol. So there's this mask of 00 followed by a bunch of Fs that gets applied to any 32-bit value that's read that contains a 24-bit address. And if you search for any function that contains that mask, it's related to the DMR networking code. So that lets you sort of separate like all of the flash I/O code from all of the serial port I/O code from all of the networking code. You then need to find the audio codec code that actually compresses and decompresses the sound. So DMR audio uses the MB+2 codec. And the MB functions use shorts. They use 16-bit values, even though the registers are 32 bits wide. And they don't do any of the bit striping, which is a fancy performance hack that they could have used that this platform supports, but that does not exist in normal C code. So I dumped all of the RAM out over USB, and then I searched for large regions that contained only 0000 or 0001, and that gave me the buffers for all of the audio codec work. And then by finding every function that accessed those addresses, I was able to identify the audio codec functions themselves. Later on, I'll show you how to run those in Linux. And all of the code that targets these buffers is the audio codec. There are no false positives in this, which was particularly nice when reversing something that was not yet running in an emulator. Now, I also need to reverse engineer the USB stack, because having a cable connected to this device isn't very useful until I can actually give it new commands and perhaps modify the old commands. So Radara 2 and IDA Pro can't automatically find these functions because they're never called directly as functions. Instead, they're loaded into a table of function pointers, which get called by a USB event handler. So I search RAM for pointers to flash, and there aren't that many of them. Then I find the function in that array that has lots of 1-byte comparisons. Because the protocol has only a single byte for the command field. And then I look to see that those 1-byte functions are the same as the known commands. In my case, 2.1 is a read, 4.1 is a write, A2 is an erase, 9.1 is unique to this protocol. By finding all of those, I'm able to then know that I've got the right handler function, which sure enough pops up, accessing the right regions. And then I'm able to hook them by rewriting the function calls. For the ones that are in RAM, the runtime function pointers like the USB stack, I just boot the regular application, and then in some other function that happens early on that I've hooked, I then rewrite the pointers to point at my handler instead of the initial handler. In this way, all of the calls get redirected. My function handler sees if it's, say, a USB command that I want overloaded, and then it runs my version. Or if I don't want it overloaded, it hands control back to the original function, which is running a few clock cycles late, but is otherwise unchanged. There are also branch and link instructions, which are inside of the thumb instruction set. These are composed of 2 instructions in a row, but they can be rewritten to point to any other location that I like, predictably. So I just wrote a little bit of C code and a little bit of Python code that produces these branch and link instructions, and I use that to change the binary in place. I'm using IDA Pro and Radara 2 for my analysis, but not for my patching. I do all of that in C or Python. You also need to carve room for your own code, because this radio has 1 megabyte, and the thing about programmers is that they always grow their programs to consume all available resources. In this case, they've almost exactly filled their 1 megabyte of space. But China is number 1, and their alphabet is the largest in the world, so they actually spend 1/5 of all available internal flash memory on the Chinese font. And once you've identified this region, you can safely overwrite it as long as you are using the Latin font. So we retargeted the compiler to throw our code in this 200 kilobyte region, blowing away the original font. If you happen to receive a text in Chinese, you'll actually see little bits of the firmware image on your screen in lieu of the Chinese glyphs, because China is number 1, and Mandiant is number 2. Now you also need RAM, because your code needs to politely coexist with the original code. You're adding new features, but you're not really ripping out much of the old ones. RAM has a bit more left over, but you need to find it. So at this stage, you can sort of guess at a region of RAM and just hope that it won't crash if you use very little of it. And then you fill all of RAM with dead beef before you begin running your target application. Then after the application has been running for a while, you dump all of it out and you look for the largest contiguous region of dead beef, and that tells you where the available RAM is. In my case, I found 20 kilobytes of free tightly coupled RAM at 1000 B1000. This tightly coupled RAM cannot be used as executable code, so you have to, if you want to run any code from RAM, you have to load it into main RAM. There is a smaller region of about 3 or 4 kilobytes in main RAM that can be separately used as a different linked region. There's no virtual memory here, so everything is stuck at a fixed address, but this is actually helpful to you as a reverse engineer because things don't move around beneath your feet. A global variable will always be at the same position for the same firmware revision. You also want to port symbols. So you have function calls in, say, AMD64. So let's say that you've got this function and you need to know what other functions are the same thing. do these equal each other by the machine code. Unfortunately, you have lots of move immediate instructions, so you need a full disassembler in order to know which bytes in the left column you can ignore. In ARM, the immediate values aren't as useful, so they're not used as often. In this case, those 3 lines at the bottom are what's called a constant pool. Those are data addresses that are being loaded, or values, or function pointers, it could be all sorts of things. But the special thing about them is that the compiler actually pushes them after the return instruction. So they're not inside of the function itself, which means that you don't have to worry about them when you're comparing 2 functions for equality. Now, inside of the function, you have a branch and link statement, which is actually used to do the function call from one function to the other. Those always have EB as their most significant byte in 32-bit instructions. And in thumb, they always begin with an F. So you can just throw away any half word that matches where they both begin with an F, but the other bits are different. You just throw it away and you pretend that they were equal. And this allows you to compare 2 functions for equality without a proper disassembler. We use it in production, and it's just this teeny little do-while loop here with nothing more complicated. This function takes a source address and a destination address, and it just tells you if the functions are, how similar they are based upon a score. Now, you also want to do firmware emulation, because when you have a firmware image and you're changing it, you need test cases or you will break your features. At the same time, you don't want to have to run it in the physical hardware, because that requires that a human being sit down, take a laptop, take a radio, plug the cable in, install the firmware, and then repeat it for each of the other 3 revisions in order to find out at the end that a feature broke a month ago. So what you can do is you can just relink it to be a regular Unix application. In this case, I've made an executable program called MD380EMU, which is the MD380 radio firmware wrapped into an ARM Linux executable running through QEMU on my AMD 64 laptop. There are 2 ways to do this. You can use mmap, which conveniently allows you to load a file into RAM at any particular address. So you can tell mmap that you really want the firmware loaded into RAM where the firmware would normally be in the radio, and you want it to be from the firmware image, and you want it to be executable and writable. And then it will load it into memory at the right location. You are in an ARM Linux environment, so you can natively run all of the functions. You can just take the address, cast it as a function pointer, and call it, and it will work. The other way to do it is through Obj Copy. You can produce an elf.o file, and this .o file contains the firmware, or contains a live RAM image with the appropriate section name. In this case, I call one of them firmware, and then I call the other SRAM. And then I use my C compiler to link them together, and I tell the compiler that the firmware section needs to be where the firmware ought to be, and also that the SRAM section needs to be where the SRAM ought to be. This produces a functioning ARM Linux executable, and in Linux, if you install QEMU user or QEMU FMT, Linux will automatically recognize that the thing you're trying to run is for a foreign architecture and call the appropriate handler. So you can run a windows.exe file from the command line, and Wine will automatically emulate Windows, or you can call an ARM Linux executable from the command line, and QEMU will automatically translate it while keeping all the system calls intact. So it's accessing your same file system as the same user from the same environment, but with ARM instructions running the firmware. And I can use this to reverse engineer and port my application. In the case of this screenshot, I'm actually taking an audio recording that was taken as raw packets off the air with my packet sniffer, and then I'm converting it to a normal WAV file that I can play on my laptop. I've gone through this a bit quickly, but I hope that you've all had a good time and learned some tricks. I have some more tricks to share, which I would prefer to do over beers and in good conversation. In the meantime, though, does anyone have a question that they would like to ask? Okay. Oh, yes.
So you did all this to connect the device?
Yes.
What did you add?
So we added, so you've got this radio, you've got a phone book for your own users, right? So I add my buddy Oxa to it, I add my buddy Alex to it. I've got all my buddies loaded into my phone book, but that's only like 20 people. When I get a call from a stranger, and amateur radio is very much about talking to people that you don't already know. Say I get a call from Ralph in Tennessee. Ralph is insane, so he's not in my phone book. He's obsessed with like ways to use wasp spray in self-defense, which he thinks is legal because there might be a wasp. So if Ralph calls me and I don't already have him in my phone book, with our firmware patches, we're able to use the unused region of external spy flash. We have 15 megabytes free. We store the registration logs of all 35,000 amateur users of this protocol. So Ralph's name will pop up. It'll say, this is Ralph. His call sign will pop up, his city, state, and his country, so I'll know that he's also from Tennessee, so that I can speak Tennessean with him instead of American television English. Similarly, if someone calls in from here in Croatia, I'll know that it's Croatian by the caller ID record on my screen without having to remember that Croatian amateur radio call signs begin with 6A. We also added a promiscuous mode so that you're able to listen in to conversations for groups that you're not a part of. This is very handy when you're traveling and you need to know what chat room number the locals use in order to jump in and say hello. We also added promiscuous sniffing for the raw packets so that you can run a USB cable from your radio to your laptop, and then you can capture all of the audio and all of the data that comes by to a record on your disk that you can later analyze. You can see that Ralph talks to Mike, so maybe you don't want to hang out with Mike because he might spray you in the eyes with wasp spray. I'm kidding. Mike is a gentleman, but Ralph would totally do that. Yes?
Have you sent the patches back to when?
So all of the code, all of the examples that I've shown you, all of this is open source. We have a project on GitHub. The manufacturer is aware of this project, but politely remaining indifferent to it. So they've not accepted any of our patches back into the main distribution, so far as we know. They are, of course, welcome to do it. The licensing for this project is that if you enjoy the project, you are required to buy me a beer. It has to be an IPA, though. Your license gets canceled if you try to make me drink a Pilsner. For good reason, you know. I mean, I've got to get paid. Greyhound don't run on water. Any other questions? Great. Thank you kindly.